Hi everyone, this is Shahnur Alam Shourab. Following our previous webinar, which we could not complete due to an IT issue, we have decided to record this webinar, and I hope this will be useful to some of us, if not many. Condition assessment of an existing structure is a very broad topic. So in this presentation, I will go through some of the common defects that we usually see in the concrete structures, and I will also talk about how we can address or how we can identify those defects and how we can inform our maintenance strategy. Uh, I should mention here this presentation is based on my experience here in the UK and in Ireland. So I will refer to in many cases, I will refer to the British standard or National Highway DMRB standards or any other standards that are in use in this region. Yeah, before I start on to the main topic, I will briefly share this safety bulletin from National Highway. So this incident had happened 2 years ago when two persons decided to travel back home after a night shift rather than using their pre-booked hotel. The investigation later on concluded that the incident happened due to a fatigue-related issue which had led to a microsleep or loss of concentration during the driving. I know for the nature of our work, we need to travel a lot. I hope everyone will be safe while traveling to and from site as well as while working on site. So these are the topics I will discuss today. I'll briefly talk about why and when we do the condition assessment. As I mentioned, I'll talk about some of the common defects and durability issues, including cracking, reinforcement, corrosion, and I'll briefly touch on the chemical deterioration process of concrete materials. I'll discuss about how we can proceed the condition assessment, including in situ and lab testing. I will also give some examples of case studies that we had done in the past. So here's the definition of concrete structures. According to EN 1992, a durable structure shall meet the requirement of serviceability, strength, and stability during its design life. But also there is another thing here which is important: without significant loss of utility or excessive unforeseen maintenance. According to ACI 201.2, which has a kind of similar definition, durability here is defined as its ability to resist weathering condition, chemical attack, abrasion, or any other process of deterioration. So durability issues in concrete structures can occur for various reasons. It can be due to excessive cracking or deflection, which can be the result of excessive loading. It can occur due to reinforcement corrosion and spalling, chemical deterioration of concrete material itself. It can occur due to fire damage as well. Here are some photos of durability issues that I have encountered in my work life. The top left photo shows concrete spalling and reinforcement, exposed reinforcement in the in the beams of a bridge which has been affected by vehicle impact loading. The middle picture on the top shows the concrete spalling with exposed reinforcement as well as exposed duct and tendons. So I should say this beam is a post-tension beams. So these ducts and tendons are crucial to their overall capacity of the structures. So in this case, it's already been exposed where duct and tendons had significant section loss and fractures as well in certain locations. In this picture, you can see the spalled concrete showing the soffit of the steel beams due to, on the decks of it in a railway tunnel. This is a photo of the spalled areas of a fire damaged building. And the last picture on the right bottom shows the ruins of a building or a fort. This was probably once lived by very important people. Over time, it has gone completely inhabitable. So why and when we do condition assessment? So we do condition assessment to establish the current condition of and performance of the asset. If we identify any defects or degradation or deterioration process that is happening within the concrete, we want to know the severity and extent of these defects. When the performance does not occur as to the expected service level, where there is limited information or we don't have any information. So for example, we don't have any design information or we don't have any uh, um, uh, uh, design drawings or as-built drawings. We do the condition assessment to inform maintenance, repair, or intervention strategies, or also we do when the structure goes through the process of change of use. Overall, we do the condition assessment to optimize the whole life cost and asset values. So this is the slide. I'll talk about the performance and the overall maintenance cost as as the structure ages with time. So in the beginning, we expect the performance of the structures to be high, obviously above the performance threshold. As the structure is in service, the structure will undergo the process of deterioration. During the initiation phase, this deterioration will be minimal, and at this stage, the maintenance cost will be minimal also. As the structure progresses into the propagation phase, degradation process will start to accelerate, and at this stage we need to intervene to determine what's going wrong with the structures, and the maintenance cost at this stage will be high as well. As the performance goes beyond the performance threshold, this is where the structure becomes unreliable. So this is when we need to replace the structure, mainly. So at this stage, the cost of any intervention activity will be greater than the replacement activity. So the main takeaway of this slide is that um, uh, the timely intervention is needed before any significant deterioration that can occur in the structure to keep the maintenance cost low and maximize the asset service life. So what are the typical defects that we usually see in the concrete? So the reinforced concrete has two separate elements. One is the concrete, another is the reinforcement. So the concrete can undergo various different mechanisms to to uh, to get the process of deterioration. The deterioration in concrete can occur due to a mechanical process, which can be fatigue, impact loading, or abrasion, or even from the vibration, which can occur due to earthquakes activity. The deterioration can occur due to chemical process. So at this stage, what happens is that the microstructures all within the concrete itself changes due to the chemical reaction, so which led to the low performance, or led to a stage where the concrete does not perform as to the expected level. And the deterioration can also happen due to physical process and fire. So in the reinforcement, in case of reinforcement, we mainly talk about the corrosion of the reinforcement. This can occur due to either carbonation or the other corrosive material that can corrode the reinforcement in the process. But not only that, defect can arise from other varieties of reason. So, for example, it can arise due to inadequate design or specification or lack of supervision or improper execution of concrete or the reinforcement within the structures. So I possibly already talked about this physical and mechanical loading, accidental loading. There's this internal stress which is caused by chemical deterioration process, and also when the structure is exposed to different types of environmental and atmospheric exposure condition. So this is a typical a photo that we usually use. This is a classic photo, I should say. Um, This is taken from a book of Mehta and Montero. This picture showing different types of cracking to the various different elements of the concrete structures. So this type of defects can occur from the very early age of the structures to the very late age. So if we consider plastic settlement cracking, this type of cracking or the plastic shrinkage cracking, that can occur just within few hours of concreting. If we consider reinforcement corrosion, that can occur after several years of exposure in different, obviously depending on the type of exposure condition and the quality of reinforcement, quality of concrete and reinforcement as well. Here are some typical examples of plastic, different types of cracking. Here's the plastic settlement cracking. You can see the cracks, parallel cracks that usually occurs on top of the reinforcement. This occurs basically due to excessive bleeding when the water tries to come out from the bottom towards the top of the concrete surface, and the heavy material kind of settles down around the reinforcement. This is an example of plastic shrinkage cracking that can occur basically due to low rate of bleeding, which is the opposite of why plastic settlement cracks occurs. Combine so this also combined with rapid early drying. In most cases, these cracking conditions we can avoid with proper design of concrete mix and take into consideration of the environment such as temperature or humidity at the time of concreting. Here's an example of early thermal contraction cracking. This type of cracking we can see in the vertical walls. You can see the parallel cracking in this vertical wall. This can also exacerbated by the restrainment issue between the slab on the ground and the vertical wall. Here's an example of construction related issue where the concreting was not done properly around the reinforcement chairs, which has left voiding within the concrete beams. So yeah, corrosion of reinforcement is the most encountered durability issue in the industry. Usually, the reinforcement is protected within the concrete. This is mainly because of the high alkaline nature of the concrete. Usually, the pH of concrete varies between 12 to 13.5. This is due to the formation of hydroxyl ion which is from the hydration product, which is the result of the hydration reaction. At this very high alkaline environment, a thin compact oxide layer forms around the reinforcement. This compact layer, we call this a passive layer, will further protect the reinforcement against going into the reaction. I should say the corrosion reaction. So once this passive layer is destroyed around the reinforcement, the corrosion will initiate. This can happen either due to alkalinity reduction via carbonation, and it can also occur due to chloride ingress. So once the sufficient corrosion product deposits onto the surface of the concrete will show this in the form of microcracking. Once the microcracking forms, this cracking will work as a pathway for further contaminants to get into the level of reinforcement to corrode the reinforcement in an accelerated way. At this stage, we see acceleration. We can call this as an acceleration period, where due to the formation of corrosion product onto the surface of the concrete, we'll see concrete spalling and macro cracking to occur. And during the process, reinforcement will lose its cross section. I should say about this that the corrosion product that forms due to this reaction process, due to this corrosion reaction, is up to 6 to 7 times the volume of the original steel element and water combined together. So this picture On the left bottom describes the corrosion activity. As Corrosion is an electrochemical process. There is a formation of anode and cathode. So yeah, the concrete act as an electrolyte, where through which the electrons or the ions can move through the pore solution of the concrete. I'll not go deep into the concrete, but it's suggesting there is a the picture shows there's loss of reinforcement section due to this corrosion activity on the within the concrete. Yeah, as I mentioned, corrosion can occur either due to carbonation. So we call this as a carbonation-induced general corrosion of reinforcement. A carbonation from the atmosphere can penetrate into the concrete through diffusion, so which reacts with the pore water solution that is present within the concrete to form carbonic acid. This carbonic acid attacks the calcium hydroxide, which is a hydrogen product due to the due to the reaction of cement and water. So this carbonic acid once this carbonic acid attacks the calcium hydroxide, there's a depletion of hydroxyl ion, which reduces the pH level. So initially, the pH is between 12 to 13, which can, due to carbonation, which can reduce up to 8 or 9. So as you can see in the photo on the left, the carbonation front is still progressing at this stage from the top into the concrete. So the reinforcement is well protected within this uncarbonated concrete. Once this carbonation front reaches the reinforcement or goes beyond the reinforcement is well exposed for further corrosion. So this type of corrosion we usually see in old structures where there is not much of a good quality concrete or there is high void ratio within the concrete, but we rarely see this in modern structures, modern highway structures. Usually the concrete in the modern structures they have high cement content, low water cement ratio, and have good construction quality. One thing to note is that the rate of carbonation will decrease as the carbonation progresses. Some photos of carbonation-induced corrosion. Uh, uh, so we call this as a general corrosion, as there is no distinct anode and cathode occurring in the affected region. So the corrosion will occur along the reinforcement at that particular region. Why? Yeah, sorry. So the so according to DMRB standard, which is the standard that National Highway use here in the UK, so it says, uh, uh, and one of the standards CS462, it says where the depth of carbonation has penetrated beyond 75% of the cover concrete, the risk of corrosion shall be considered to be high. So chloride-induced corrosion is somewhat different than the carbonation-induced corrosion. Now, chloride is brought to the concrete surface along with water. The sources of chloride can be de-icing salt, seawater. So that once the chloride deposits onto the concrete surface, it will percolate or diffuse or permeate into the concrete. Um, uh, Once a sufficient amount of chloride reaches the level of the reinforcement, the passive layer, as we have discussed before, it will break down, thus expose the reinforcement for corrosion to occur in presence of water, chloride, and oxygen. So this type of corrosion is not uniform, unlike what we have seen in the carbonation-induced corrosion. These are rather local in nature. So the corrosion will occur at a particular location only, forming a pit. We call this as a formation of a local anode and having a large cathode. So this is an anode that you can see, which is formed which is formed here, showing the pitting and section loss at this location, and the rest of the reinforcement and the surrounding reinforcement will act as a cathode. So the rate of reaction in this case will be very high compared to the rate of reaction that we usually see in case of carbonation-induced corrosion. So because of the high rate, there will be high rate of section loss to the reinforcement. This is a typical chloride profile that we usually see in the structures under ideal condition. So this slope of this curve will depend on the diffusion coefficient, which is a material resistance, and also with time. Once the sufficient level of chloride reaches the reinforcement level, we call this critical chloride content. The reinforcement will start corrode. So this is a typical example of chloride-induced pitting corrosion and the reinforcement. As we can see, the reinforcement section and this area has completely gone, and in some of the areas, as the reinforcement was found to be very good condition. So this is the DMRB CS462 criteria that we use to define the risk level. If the chloride content is greater than 1% by mass of cement and it is accompanied by the evidence of corrosion, that is, it can be a delamination or spalling, we consider the risk to be very high. If the chloride content is between 0.4 to 0.1% by mass of cement, and there is evidence from in situ testing, it can be half cell potential survey testing. So we consider the risk level to be high enough. If it is below 0.4% by mass of cement, we consider the risk level uh, to be acceptably low. Yeah, now on to the chemical reaction process of the concrete. So alkali aggregate reaction is an internal chemical reaction where a reactive aggregate reacts with the alkalis in presence of water to form a gel-like substances within the aggregate particle. So these alkalis comes from the cement usually, and when the gel is formed, these gels can absorb more water and expand in nature, which can lead to cracking. There are two types of cracking. There's two types of reaction. One is alkali silica reaction when siliceous aggregate is present, and there is alkali carbonate reaction when carbonate aggregates are present. The typical signs can be map-like cracking, and also we will see efflorescence at the surface of the cracks where this gel will try to come out through the cracks. But also cracks can happen over any reinforcement, or along the length of the pre-stressing tendons. As you can see, this is a post-tension beam, and the cracks occur in a longitudinal way along the line of the post-tensioning tendons. In accordance with British Standard BS 85002, typical allowable limit for when for alkalis when we have a normal reactive aggregate is 3.5 kg per meter cube, but depending on the type of aggregate, if the aggregate have a low reactivity, we can increase the allowable limit in the cement, as well as it is true for if we have high reactive aggregate in the concrete. Usually for high reactive aggregate, typical allowable limit is 2.5 kg per meter cube. I have put this information here for just for our knowledge, or for information. I've taken this information from BRE Digest 330. There is no evidence in the UK of damaging alkali silica reaction in the concrete made with normal reactivity aggregates that where alkali content is below 4.8 kg per meter cube. So another type of chemical deterioration that we see is sulfate attack of concrete. So usually what happens, sulfate can attack the internal microstructures, internal microcomponents of the concrete. So by the formation of atronite or gypsum, which can lead to cracking. So formation of atronite and gypsum can be expansive, so which will exert pressure onto the surrounding concrete, leading on a surrounding concrete, which will lead to cracking. But also it can this process of sulfate attack can also lead to softening or dissolution of any hydrated product. So the type of cation that is present that comes with the sulfate, whether it is sodium sulfate, magnesium sulfate, or calcium sulfate, these type of cations, they can affect the nature of the reaction that will occur within the concrete. Another type of reaction, not the reaction, another type of deterioration can happen as due to physical attack, which can lead, which can occur due to salt crystallization within the microstructures or the pores within the pore void of the concrete, leading to volume expansion and eventual cracking. Research has also shown that uh, sulfate not only attack the concrete, but also it can attack the reinforcement. However, there is a debate that whether sulfate alone can cause reinforcement corrosion, or it can act as a catalyst in presence of other type of corrosion, say for example chloride-induced corrosion. The sources of sulfate can be soil, if the foundation that is placed in the concrete has the soil has significant amount of sulfate in the soil. The source can be seawater. So in the sewage treatment plant, there is a lot of sulfate is being produced as byproduct in the process. De-icing salt also has sulfate as well. The EN 197 allows the maximum states that maximum allowable sulfate in concrete in fresh concrete is 4% by mass of cement. There are other types of chemical attack as well. Here is examples of acid attack, which can occur in the sewage treatment plant or sewage pipes. And also there is soft water attack can occur in the water treatment plants. And in both type of this both cases, hydroxyous cement product, this hydrated cementitious product can disintegrate it due to low pH in the surroundings. So yeah, as you can see in this photo on the left, all the reinforcement is already exposed due to the loss of cover concrete due to acid attack. And also you can see similar kind of processes in the soft water attack, where all the aggregate has spoiled from the cementitious matrix. So this slide is particularly important for to know severity of deterioration process in different relative humidity condition. Uh, if we discuss about the reinforcement corrosion, the carbonation induced reinforcement corrosion, the rate of this type of corrosion will be high when the relative humidity is at a level of 60 to 80%. The chloride induced corrosion will happen when the relative humidity is very high, up to 90% or beyond 90%. All the chemical attack to occur, water is a paramount important factor. So when we see saturated level of concrete, this chemical attack, if occurs, they will be very high. The rate will be very high as well. So we have discussed about different types of defects that we see in the concrete. Now, how we can assess this condition, how we can identify these defects in the concrete. We should mention that each assessment should be unique and may require unique strategies, but there are typical process flow that we can follow. We usually start with deck study, where we try to find the information related to the design consideration, construction history, methods, material that was used in the concrete, or how they were placed in the structures. We do visual inspection, hammer tipping survey, including crack survey. Then we come up with a plan how we can tackle, how we can use in situ testing and non-destructive testing. to inform what type of deterioration is occurring and what is the level of deterioration that is occurring. And also we sample concrete we sample from the concrete affected structures, affected elements for further laboratory testing. So we should say here the type and extent of testing and sampling will depend on the nature and extent of the defects that we are dealing with that we are dealing with in that structures. Here's a typical example of a deck study. You can see these photos here showing the reinforcement detailing in the concrete deck. And if we are lucky enough, we can get enough information about the concrete design. In this case, cement that was used was rapid hardening cement. This structure was built in the 1940s, and there is might be some information as well about the concrete mix design, how they were mixed as well. So usually during the deck study, we try to search for information in the as-built record drawings, construction records, what is the exposure condition during its service life. We go through the info, go through the any previous reports. There can be inspection reports, testing reports, if the structure has any previous repair history. And another thing we need to look for is that if there is any typical deterioration in the nearby surrounding areas or in the similar type of structures. So if we go through, if we know there's something wrong in a structure that is nearby in the similar region, we can then get as much as information possible for these structures to inform our maintenance strategy. So during the diagnosis phase, we need to come up with a plan how and which type of in situ testing we need to employ. So this slide shows a little bit about the non-destructive testing method. Uh, so the non-destructive testing method does not provide any direct measurements to any of the it can provide some of the properties, but may not necessarily provide any indication to the defect or cause of the defect or to the property that we are trying to measure. So we usually non-destructive testing methods, they're indirect methods. These methods are influenced by many factors. In most cases, they cannot be controlled on site, or they cannot be quantified, or the number of factors are too high to take that into consideration. So there is always this level of uncertainty in the test results. So one thing I would like to emphasize here is that calibration or the empirical relationship. So this testing methods needs to be calibrated with any of the any of the information that we have, either taken on site or from the record information. There are advantages of the use of non-destructive testing. Non-destructive testing can be cost effective if we can plan ahead. We can there can be it can reduce the destructive activities during the investigation process. We can cover a large areas within a limited time to get as much information as possible using non-destructive testing. So as I have already mentioned, in many cases, intended material property may not have any influence on the NDT results. So we need to understand about the applicability and limitation of the non-destructive testing we are using. So at the end, we'll need to decide what would be the right NDT in our assessment process. So I have provided some of the examples here in terms of different types of property that we can measure. So when we try to measure mechanical properties such as compressive strength, these are the non-destructive testing that we can use. There is rebound hammer, there's ultrasonic pulse velocity, there is pull-out testing. We can use this method, these entities in a single way, or we can use in a combined nature. So here is some typical example of ultrasonic pulse velocity, taking the measurements of concrete cubes. And there's a picture showing the rebound hammer in action in a concrete column. So the rebound hammer, this technique is used based on the measurement of rebound of an impact hammer. This technique can be used to inform about the uniformity of concrete, or to identify if there is any poor quality concrete present in the suspected areas. However, this cannot be used as an alternative for compressive strength determination, but it can be used to provide to get an estimation. Uh, but this needs to be correlated with the with the information that we have already. Because the equipment is so simple to use, this simplicity can be its enemy. So we need to be careful when we are assessing the results from the rebound hammer test results, because there are a lot of factors that can affect the results. As we can see, if there is a hard aggregate particle just below the surface at the impact point, it can affect the test results. If there is a void just below the surface, it can affect the test results. If the concrete is carbonated, it can affect the test results. This little graph on the right shows how variable the results can be if we compare the compressive strength results with the rebound hammer values. So the results can be very scattered. So we need to take this into consideration when we are assessing the values of the rebound hammer. So this is an EPV ultrasonic pulse velocity method. Is works based on the longitudinal wave principle. We have a transmitter and we have a receiver. Um, so uh, the wave travels between from the transmitter to the receiver. So based on that, we determine the quality of concrete. So the time travel will depend on the elastic properties and densities of the concrete. There are a lot of factors that's again affecting the test results. So in short, higher the travel time, poor the quality concrete will be. So there are a few different ways that we can use. We can use it as a direct method. We can use it as a semi-direct if the surface are like this arrangement, and we can use as an indirect method as well if the same surface has to be are to be tested. So these are the few test methods that you can use when you need to know about the reinforcement layout in the structures. There is ferroscan and concrete cover meter. There is ground penetrating radar. There is ultrasonic tomography, pulse echo, and also we can use impact echo as well in certain cases, depending on what we are trying to achieve from the assessment. So this little picture shows the GPR photos showing the reinforcement layout. The reinforcement are graded in a pretty good way. This is not the usual case that we see in the in on-site condition. In most cases, the GPR results will be very difficult to interpret. So it needs proper training and proper expertise. Has a photo of a cover meter showing how the cover is varying along the length of the cover meter measurements. So yeah, and this is an example of the ultrasonic pulse echo, so which is showing the reinforcement. These blobs on the top, kind of showing the reinforcement locations, and this red blob on near the bottom shows the overall thickness of that particular concrete element. Here's the slide. I'll go through this slide pretty quickly. This slide shows how the GPR works. GPR works based on the electromagnetic pulse. So this can be used to image the surface, anything below the concrete or anything below the soil. So in most cases, when it comes to doing the GPR in reinforcement, we can see this type of parabolic shape when GPR signal interacts with the reinforcement, um, because um, uh, because the reinforcement is has sort of an infinite dielectric properties. So this is the term dielectric properties of material we use when we employ the GPR. So what happens when there is a variation in the dielectric properties in the materials? So some of the signals will be reflected back to the receiver. So when it comes to the reinforcement within the concrete, so the ratio of these two dielectric properties of the material is infinity. So in that case, most of the GPR signal will be reflected back at the surface of the reinforcement. So within concrete, we should be able to easily defect the reinforcement depending on the depth of the reinforcement and depending on the quality of the reinforcement as well. So we should mention here that the GPR data can be sensitive to moisture content, chloride content, and height void ratio in concrete. Sometimes it can be very difficult to interpret the results if the reinforcement is heavily congested in a particular area due to the signal will overlap at that location, leading to inconclusive data. Ultrasonic tomography, this works. So the theoretical principle behind this is similar to ultrasonic pulse velocity that we have already discussed. However, there's a difference in the type of the type of waves that this particular type of equipment use. This equipment is based on the use of shear wave principle. So here you can see there signal transmitter and signal receiver. Once the signal is reflected at the surface of the defects or the void within the concrete, it will be reflected back, and based on that we can this equipment can produce a 3D internal geometry of that particular concrete element. Another thing is to notice that this shear wave principle works better because there is less attenuation in the concrete being heterogeneous material, and also this has got better sensitivity to any cracks or voiding. When it comes to measuring durability properties, we employ some of these testing methods. We employ a half cell potential. We employ linear polarization resistance. We try to do concrete resistivity. We try to do permeability. So I should briefly talk about one or two of these. Um, so a half cell potential is a non-destructive electrochemical method that we use to evaluate the corrosion probability. I should say active corrosion probability in the steel reinforcement that is present within the concrete. It measures the electrical potential difference between the internal concrete and a standard reference electrode that is placed onto the surface of the concrete. This is the one here we're talking about. Here, concrete acts as an electrolyte. If the steel begins to corrode, it will create a electrical potential. So in this case, the more negative the voltage reading, the higher the probability of active corrosion. So we can use to determine whether the reinforcement is actually corroding within the concrete. However, it does not provide the rate of reaction. So in that case, we use concrete resistivity. Although concrete resistivity does not give us a direct rate of that corrosion activity, but it can provide a qualitative assessment in the process. So, the process the concrete resistivity works um, is that how resistive the concrete is against the flow of electric current. So this will provide an indication of the about the quality of concrete. So the good quality concrete will have good resistance, poor quality concrete will have poor resistance. This concrete resistivity testing method can be affected by various different factors. One of them is if there is high moisture content, that will ease the flow of current in the concrete. As we have seen previously in one of the slides, that a high in presence of uh, high relative humidity, the corrosion will also occur at a higher rate. So so we can say that the higher the resistivity of the concrete, the lower will be the rate of concrete. This is how it works. We also do permeability testing of the concrete cover, because concrete cover will ultimately the permeability of the concrete cover will ultimately determine how easily the contaminants from outside can get into the concrete. Here is the typical values that we use to determine the probability of still. This is a table taken from ASTM 876. If the value is greater than towards the positive side, we can say there is less probability of corrosion to occur. If the value is between minus 200 millivolt to minus 350 millivolt, or we can say the reinforcement, there's a possibility that the reinforcement is corrosion is occurring, but however it can depend on many other factors. If the value is less than 350 millivolt towards the negative side, so there is we can say there is a high probability of corrosion in this case. But these results will be affected by many different factors. One is the moisture content, obviously, presence of chloride in the concrete, and also the level of oxygen present at the level of reinforcement. So I should highlight this here. If the concrete is saturated and so saturated concrete means that there will be very limited oxygen to be present within the concrete. So at this stage, in this type of scenario, we'll see the potential values to be very low. It can be in the range of minus 1,000 to minus 9,000. In case of dry concrete, so the potential values usually be towards the positive side. So in dry concrete, if there is limited water present, there will be limited corrosion as well. So these are the typical methods that we typically employ when it comes to structural quality: rebound hammer tapping, rebound hammer itself. So this is the hammer tapping survey to find out delamination in concrete. This is separate. This is rebound hammer is separate to rebound tapping. We can employ ultrasonic tomography or pulse echo. It can provide us information about the relative quality, voiding, or it can measure element thickness. Impact echo, we can employ impulse pulse response. This is not particularly we see in use in the industry. It is a very useful tool to provide a quick screening of the flaws or any defect or any suspect area in the region that we are testing. It can however, once it identifies the suspect areas, this needs to be confirmed by further investigation. We can do concrete resistivity. I should say the concrete resistivity is particularly important when it comes to concrete quality, but also it can provide us information about the qualitative rate of corrosion. We have talked about the permeability methods, relative quality we can get from the permeability methods, infrared tomography. So yeah, in majority of the case, if we combine two or more NDT, this is my preference. This is the best approach when it comes to identify the structures quality in the concrete. So yeah. On top of those in situ testing, we need to consider for lab testing as well. So in many cases, we need to determine the level of contaminants in the concrete to assess the level of deterioration that we are expecting in the concrete, or to assess the a level of risk that is present at at that time of testing. So we usually do chloride content testing. We usually collect samples at different increments. Usually it's 25 millimeter increments up to a level of 100 millimeter, but that depth can vary, and that depth of increment can vary as well, depend to suit the requirement on site. We do cement content test, we do sulfate content, alkali content, or we also do petrographic examination. So the petrographic examination can provide us information about the deterioration mechanism that is happening right now within the concrete. It can provide us information about if there is any evidence of sulfate attack or alkali aggregate reaction that has happened within the concrete, or any other chemical deterioration that alters the microstructures of the concrete. It can also provide us information about the quality of the concrete, degree of hydration, voiding, type of aggregate that is being used in the concrete. So yeah, it can. There's another thing, another most important thing when it comes to fire, to determine the depth of fire damage. Petrographic examination is the one of the best approach to determine the affected fire affected elements. So here's some case studies. This is a column that I've encountered in a building here with poor construction. So we found this poor concrete in several columns in that floor. So we had to employ a strategy to determine the compressive strength of the concrete, as well as to determine the to relative quality of concrete compared to the good qualities of the concrete. This is an example of concrete spalling and corrosion of reinforcement and post-tensioning systems. This is I have already talked about in one of the photos previously. This is where the concrete pier is getting affected by the water leakage from the damaged from I should say from the damaged uh, uh, deck joint on top of the bridge. So water is leaking through the deck joints. Because the road on top is highly salted, all this water contaminated with salt and having chloride and sulfate is getting in onto the concrete in the pier, thus this causing this delamination and reinforcement corrosion. This is a photo taken from a bridge that has extensive cracking, and the bridge is a post-tension segmental joint. You can see the segmental joints, and these are the segments that are connected by the post-tension elements. So there was extensive cracking in this type of in this particular bridge, where we have proceeded with the recommendation for further crack monitoring. I'll now talk about this concrete pier to have a case study. So once we determine, based on the inspection reports, that there is a lot of delamination is happening in the concrete, so we already know in this case this corrosion is the problem due to the water leakage from the road surface on top. So we undertaken corrosion testing. This included delamination testing, delamination survey. We have undertaken concrete cover, half cell potential survey, concrete resistivity. We have undertaken depth of carbonation. We've undertaken chloride content at several incremental depths in order to know the level of chloride in the concrete at different depths. We have also undertaken cement content, sulfate content, and alkali content to determine if there is any risk associated with sulfate or alkali related deterioration. As an example of a half cell potential survey, This contour plot is showing the red, the locations in the red and yellow is kind of typical, showing that where there is high probability of reinforcement corrosion. So this is the location where this grid A1 is. So this is the location where this grid A1 is. As you can see here, this half cell potential survey should not be undertaken in the already delaminated areas. So we're still we can from this half cell potentials survey, we are seeing that even beyond even away from the delimited areas, there is a probability of corrosion. So there is high probability of corrosion is occurring at these locations here. There is a typical example of how we can get information about the remaining section loss, or I should say remaining areas of reinforcement. In most cases, the reinforcement starts to corrode from the surface, from the outer surface. So so if we take measurements, take this y value, this will not provide any information whether that particular reinforcement has a section loss or not. So in order to get a full picture how much section that reinforcement has lost, we need to take this measurement x as well, and this is how we can calculate the remaining area of that particular reinforcement. So this is another case study. In this case, we determined the deck slab thickness. In this case, we have employed ultrasonic tomography. We did not had any information about the thickness of the deck. However, we had a layout information how the deck is supposed to be, and we determined the thickness is kind of based on the results of this ultrasonic tomography, which kind of matched what we are expecting on site. One of the major challenge was when we used this ultrasonic tomography was to calibrate the data, because there was a lot of variation in the concrete quality, as we can see, voiding and reinforcement corrosion as well on the soffit of the deck. So, yeah, here we should mention that I should mention here that I did not we could not employ GPR to get the element thickness, mainly because there is highly congested reinforcement on the decks of it, as well as there is a lot of voiding that did not help the GPR data. So here is another example. This is the last case study. After that, I will finish. So this is a fire damaged deck slab, a concrete slab in a fire damaged building. So due to the fire, there was evidence of concrete spalling. There was evidence of delamination as well. There was evidence of micro cracking just outside the region of this spalling. So in this particular case, we had to undergo several few techniques to determine how much is the affected areas in the concrete slab. So there was we conducted delamination survey. We conducted ultrasonic pulse velocity, both direct and indirect method. We conducted ultrasound tomography. We conducted a rebound hammer survey to determine if the quality varies in the concrete as a result of the fire damage. We took concrete course for petrographic examination, and we had taken a few courses to ensure that the concrete strength has not been affected by the fire. So at the end, we came up with a damage class where the concrete was classed from D0 to D5. D0 indicating there was no damage. We don't see this in the picture here. And D5 where there is extensive spalling with significant depth. So based on the damage classification, we then had to come up with a repair strategy. So in case of damage class D5, it was decided to go with a structural repair to expose the reinforcement and to replace the concrete beyond the depth of the reinforcement. So yeah, before I conclude, I would like to conclude with this slide. this slide shows the role of testing within the structure's maintenance process to ensure safe and durable existing concrete structures. The maintenance of this of the existing structures can be divided into three phases: condition monitoring phases, diagnosis phases, and the solution development phases. And in each phase, testing and monitoring has its role to play. Assessment of the structural condition, or we can say the finding to find the cause of deterioration and the extent of deterioration is important before carrying out any repair activity or maintenance activity. Even after the repair, even after we did the repair activity, the performance of the repair should be monitored to confirm the adopted repair strategy is working correctly in the structures. So with this, so yeah, thanks everyone for listening this far. It was a long presentation, 1 hour. So yeah, if you have any questions, here are my contact details. Please let me know. I'll try to answer any question within my capability, and it would be good to have some discussion. Yeah, I'm looking forward to your emails or message in the LinkedIn's. Thank you very much. Thanks everyone.